didn't mean that to be so loud. One thing you probably remember, hopefully you remember, when we looked at the substitution rule, we said that this is parallel. The substitution rule for integration is a technique parallel to the chain rule of differentiation, right? Basically, we use the substitution to undo the chain rule. So in these parallel techniques, you're going to see it also in integration by parts. So here we go. Let's write parallel techniques, and we are equating techniques in differentiation to integration technique. Differentiation and integration. So the first one, we saw that when we use the chain rule, then the operation that is parallel to the chain rule was the substitution. And if you recall, we have also a rule for product. So the integration equivalent to the product rule of differentiation is integration by part. So let's see. Let's do the let's differentiate using the chain rule. The product rule. Okay. Let's say we have two functions f and g, and we want to differentiate the product of f times g, like so. By the product rule, it will be f prime times g plus f times g prime. Okay? Now, this is as far as differentiation is concerned. What about integration? Well, we want to undo what we've just done. So, on the left side, if we integrate the left side, then we undo the integration, so we end up having f of x times g of x. On the right side, remember, we integrate. So we integrate the sum. But the integration of a sum is sum of integration, right? So it will be the integral of f of x, f prime of x, this is f prime, gx, dx, right? So the integral of f prime times g dx plus the integral of f of x g prime of x dx. At this point, and I'm doing something differently than I did in the morning, at this point I'm going to do substitution. If you recall, when we learned this in Calc 1, we use also we either use the FG notation or the UV notation. And let me change to UV notation for reason that will become clear momentarily. Okay, so we'll do the following. Let U equal f of x, and from here, and v equal g of x. If we do this substitution, then du, the differential du, will be, remember, du dx is f prime, right? So du by itself will be f prime dx. And dv, the differential dv, since v is g of x, dv dx equals g prime, and dv is g prime dx. And now you can see the motivation for doing so, because on the right side, if you see, I have f prime dx and I have g prime dx. So writing this differential du and dv will allow me to simplify the expression. So now if this was the equation star, so we can write this equation in the following form. Instead of f times g, we have u times v on their left side. And now, instead of the integral of f prime times g dx, we can look at it by the commutative rule. We can write it as g times f prime dx, right? So it would be, let me rewrite it just for sake of clarity. Okay, this thing is du. And then we have the integral of f of x times g prime of x dx. And this thing is dv. And of course, this is v and this is u. So, we end up having, it's the integral of v du plus the integral of u dv. Okay? Now, let's say we have an integral that looks like the integral of u dv. If I want to solve for that, then the integral of u dv going to be uv minus the integral of v du. And this, folks, is the integration by part rule or technique. Very clever technique, and you'll see the usefulness in a few minutes. But before we go and practice these pearls of wisdom, I want to give you a list of 10 common integrals. And before you're going to ask me, do we need to learn it by heart, or can we have this list available to us in the test? The answer is yes, you need to learn it by heart. No, the list will not be available to you on a test. Okay? So what are those integrals, common integrals? So on page 2, we have a list of common integrals. I think there are 10. I didn't count it. I didn't count them, but it goes like this. We'll start with the power rule. The integral of x to the power of n dx equals x to the power of n plus 1 over n plus 1 plus c, provided that n is not equal to negative 1, right? Otherwise, we cannot do it. The second will be, what happens if n equals negative 1? So x to the negative 1 is 1 over x. So the integral of 1 over x dx, well, we know it's the natural log of the absolute value of x plus c. And then the next one is the exponential integral. The one that we love the most is the integral of e to the x, as it is e to the x itself. If the base is not e, then we're dealing with the integral of a to the x. Well, the result would be a to the x divided by the natural log of a. And then we have a bunch of trigonometric stuff. Start with the sine and the cosine. And see if you could figure this out. Continue with the secant squared and cosecant squared. and wrap things up with the integral of the secant times the tangent and the integral of the cosecant times the cotangent. Okay? So what do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I probably could have added to this 2 or 4 more that have to do with the inverse trigonometric functions that you also probably want to remember. All right. Okay, call it out, please. The integral of sine x, the integral of cosine, the integral of secant squared, the integral of cosecant squared, negative cotangent, very good. The integral of secant times tangent, and the integral of cosecant times cotangent, oh, negative cosecant. Okay. What else would you add to it if you had room? I would add the integral of dx divided by 1 plus x squared, which is the inverse tangent. Okay, and also some stuff associated with the inverse sine or the inverse cosine. But you know what? We'll get to it in a hurry in this chapter anyway. So, okay, so this is the end of this introduction, the introduction to this technique. And from this point on, we're going to practice.